This is section 9.8, power series. So we've talked about different types of series and the conditions under which they converge. P series converge for p greater than 1. Geometric series converge for absolute value of r less than 1. So here's another type of series called a power series. So here's the definition of a power series. The sum from n equals 0 to infinity of c sub n x to the power of n. All right, so these sums start with 0. So technically a sequence always starts from 1, but we talked about you can sort of adjust that and fudge that around a little bit depending on how you want to define things. So the reason we do that is so that the first term of this sequence is linear. It's just whatever C0 is. All right, and then your next term, this term actually is the constant term. Because it's x to the 0. So that's why we need to start with 0. So first term would have x to the 0 be a constant term. Then the next term is linear because it's c1x, and then your next term is quadratic, c2x squared plus etc. All right, so this looks pretty weird, but if you think about it, you know, a polynomial, like if you think about a polynomial, right? Let's think about even like a quadratic polynomial. So I could call, usually we call it ax squared plus bx plus c, right? Well, what if we called it c0 plus c1x plus c2x squared? See, it's just renaming things. The a is the c2, the b is the c1, the c is the c0. So what you really have here is a polynomial, and the c's are the coefficients of the polynomial. Unlike a polynomial that's quadratic and has 3 terms, or could have 4 terms, a polynomial could have 5 terms. All right, this is basically a polynomial with infinitely many terms. And just like a polynomial like ax squared plus bx plus c is actually a function of x. So for example, you know, 3x squared plus 5x plus 2. All right, we can consider that to be a function of x. It's a function. All right, likewise, these are also functions of x. So for a given series of coefficients, that's, so c is for coefficient, these are the coefficients. So for a given sequence c sub n, the series is, I'm going to use my least favorite word, it referring to this stuff up here, it is a function of x. As such, it has a domain. The domain of the function is the set of numbers x such that the sum cn x to the n converges, because it's not always going to converge. All right, so that's all a little weird and abstract, but so let's try to make it a little concrete. We're going to look at our first specific example of one of these. So the easiest thing you can do, well, all right, the easiest thing you could do is have all the C0s be 0, and then the power series is just 0. So the next easiest thing you can do is have all of the CNs equal 1. And then what you have is the sum from n equals 0 to infinity of cn x to the n is just the sum from n equals 0 to infinity of x to the n. And that's actually our familiar geometric series. So geometric series is a special case of the power series, a special kind of power series. So we know that this is geometric, and we know that it converges for absolute value of x is less than 1. As long as the absolute value of x is less than 1, it converges. But we know more than that. We also know that the sum from n equals 0 to infinity of x sub n, we know what the sum is. It's 1 over 1 minus x. That's just our sum for geometric series. So what we're going to say about that is that the sum from n equals 0 to infinity of x to the n represents the function f of x equals 1 over 1 minus x on the interval absolute value of x less than 1. So if absolute value of x is, so these two things are equal as long as the absolute value of x is less than 1. If the absolute value of x is more than 1, then they're not equal. So we call negative 1 to 1, that's this right here, it is called the interval of convergence. Interval of convergence of the sum of this series. And what is going on graphically is that if you think about what the graph of 1 over 1 minus x is, well, you know what the graph of 1 over x is. This is a reflection over the y-axis, and the 1 is a shift left. You can also analyze this by asymptotes. This graph has a vertical asymptote at x equals 1, has a horizontal asymptote at x equals 0, and it has a y-intercept of 1. So basically the graph looks like this. All right, this is an odd asymptote, so the rest of the graph looks like this. This is what the graph looks like. So on this interval of convergence, -1 to 1, which means from here to here, the series is the same, it's the same as the function if we do infinitely many series. So the infinite sum, it models this whole part of this graph. Now, if we're outside the interval of convergence, the series doesn't even converge, so it doesn't model anything. But inside the interval of convergence, the series and this rational function are the same. That's important because the series is like a polynomial, but this is a rational function. It's not a polynomial. So the key to all this power series is that we can use something that is like a polynomial to model something that's not a polynomial. So we're going to see a little bit more about graphically what this means in the next video.